Hi, everyone, and welcome to Lesson 2 in Unit 5. And again, this is a very condensed Unit 5. I'm trying to just touch on the major issues so that you guys are aware of what it's like to work with gases in terms of chemistry. And so today in Lesson 2, we're going to cover what we call the ideal gas law. And so it's a progression that we're building from last lesson. And it's just adding one little piece to the puzzle, and then our last lesson, which will be next week, we'll pull it all together and do stoichiometry with gases. So one thing I wanted to do was a quick review of what we did from the first lesson, and essentially we covered these three laws, and then we put them together, and so Boyle's law relates pressure and volume, and we got this P1 V1 is equal to P2 V2. Okay, and essentially what we determined was that pressure and volume are inversely proportional, and so this relationship yielded this equation, this law. But it kind of makes sense, and I hope you guys are, when you think about it, is that the higher the pressure, the smaller the volume, or vice versa, the smaller the volume, the higher the pressure. And so sometimes if you just think logically about it, it gets you to the to the law that they're trying to develop. Okay, Charles's law related volume and temperature, and what Charles's law said was V1 over T1 is equal to V2 over T2. And essentially, as a proportionality statement, its temperature is proportional to volume. The higher the temperature, the larger the volume. And so if everything else is kept constant, that's the one thing I want to emphasize here, that in Boyle's law, obviously temperature and the number of moles are kept constant. In this case, pressure and the number of moles are kept constant. In that situation, if you increase the temperature, you have to increase the volume. Okay, Gay-Lussac's law is that P1 over T1 is equal to P2 over T2. And again, what they proved was that pressure is proportional to volume. That proportionality statement yields that law. Okay, so that's a direct result. And in this particular case, temperature and the number of moles are kept constant. And finally, what we did in the last lesson was we put them together, all these laws together, into one law and called it the combined gas law. And we said P1 V1 over T1 is equal to P2 V2 over T2. And so this allowed us to calculate, if you are given 5 things, you can calculate the 6th thing. So look at this. Let's say you were given the initial state, the initial pressure, the initial volume, and the initial temperature, and then you were given let's say the final pressure and the final temperature. You could calculate your final volume using this combined gas law relationship. So this is that's kind of how we finished the last lesson, was putting these laws together into what we call the combined gas law. All right. A couple of other quick things I need to do before we get into the main part of today's lesson. There was one law that I didn't cover last time, and it's called Dalton's law of partial pressures. And this is actually a fairly straightforward one. It says that the total pressure in a vessel is the sum of the individual pressures from all of the component gases. And so if you had a container and in it you had, I don't know, this blue gas, and you knew its pressure, and you had another substance, it was these red dots represent the second substance, and maybe we had green dots representing a third substance. If I wanted to find the total pressure in the container, I would just add up the individual pressures created by each of those separate gases. And I think it kind of makes sense. I'm hoping you guys will look at that one and go, well, geez, that didn't, you know, that's pretty obvious or self-evident. And it has some implications that are a little bit more complex, but I wanted to make sure that you understood that that's what we call Dalton's law of partial pressures, that all you have to do is add up the individual pressures to get to the total pressure. The other thing I wanted to cover is that if you're ever, they have two conditions here. One of them is called STP and one of them is called SATP. And STP is standard temperature and pressure. And they tend to use it a lot in questions. Standard temperature and pressure, if they ever quote that, you know that it's 0 degrees Celsius, and you know that that is equal to 273.15 Kelvin. But also, you know the pressure is 101.3 kPa, which is 1 atm. All right, sorry about that. Forgot to put my phone on mute. Standard temperature and pressure, just know that if they ever quote it as STP, you know at that point that the temperature is 0 degrees Celsius or 273.15 Kelvin, and you know the pressure is 101.3 kPa or 1 atmosphere of pressure. Okay, but the other one is a standard ambient temperature and pressure, which again is just another kind of standard that they tend to use. And for this one, the temperature is 25 degrees Celsius, and that is 298. Oh, again, I apologize. I don't get phone calls all day, and then I've had 2 in the course of this lesson, so my apologies. Temperature is 25 degrees Celsius or 298.15 Kelvin. And at standard ambient temperature and pressure, the pressure is 100 kPa. So it's a little bit different. The pressure is just a little bit different than STP. So anyway, if you ever see questions that say that it's at STP, you know that you are being given a temperature and a pressure. Okay. All right, let's move on here to the main focus of today's lesson, which is the ideal gas law. So one thing I want to emphasize is that in all of the stuff we did in lesson 1, the amount of gas in the container did not change. It was, in other words, it was a sealed container. So you can think about it as a box. Now, this box could have a movable like piston on it. Like, in other words, I could put pressure on this and make it smaller. So I could change the volume of this box by pushing down, and that would make it smaller. So I could do that or make it bigger. But essentially, the amount of gas in the container, and I'll just show it with red dots here, doesn't change. So I just want to emphasize that, is that we changed the temperature, we changed the pressure, we changed the volume, but we did not change the amount of gas. Well, now we want to investigate what happens if you change the amount of gas, and that was another law, and this is called Avogadro's law, and basically it's the impact of changing gas, or the amount of gas. And I'm hoping that you guys are going to find this quite again self-evident. And what it is Avogadro's law says that the number of moles of gas in a container is proportional to the volume. So in other words, if you increase the number of moles, that you will therefore increase the volume. And I hope you guys kind of go, yeah, that makes sense. You know, like if I were to attach a little hose and pump in a bunch more red dots into this container, it's going to make the volume bigger because, you know, it's going to allow the container to expand a little bit. Because more molecules bumping into the container walls more, it's going to increase the volume. So this yielded what we call Avogadro's law, And as a result of that, we have this relationship. V1 over N1 is equal to V2 over N2. Very similar to the other directly proportional relationships. And again, if you forget how that happened, essentially we could divide the number of moles off one side, and you'd have V over N is equal to a constant value. And so regardless of which volume and which number of moles, it would always be constant. And that's why this relationship holds. Okay, well, here we go, is now the ideal gas law. So let's now add in Avogadro's. And if we add in Avogadro's law to the other three gas laws, you end up getting this. P1 V1 over T1 times N1 must be equal to P2 V2 over T2 times N2. But what's interesting is that we're not always given two different states of the same gas. So what we essentially know is that for every pressure and volume and temperature and number of moles, it must be equal to some constant. Okay, and this is the beauty of the ideal gas law, is that we have calculated what that constant is, and we've called it R. We've called it R, and essentially, R is equal to 8.314 as long as you've measured your pressure in kPa, you've measured your volume in liters, you've measured your temperature in Kelvin, and obviously the N would be in the number of moles. Okay, so as long as you use those units, the constant for any ideal gas, and I'm going to talk a little bit more about what it means to be an ideal gas in a second, but any ideal gas will have this as their K, all right? And so as a result of that, we can actually get this relationship where PV over NT is equal to R. Now, I have to admit that in most cases, they rearrange this a little bit, and they put the NT up with the R, and you get PV is equal to nRT. But essentially, really, it has come from that initial equation. Okay, so here it is, PV equals nRT. Always convert to Kelvin, use number of moles, use liters, and essentially, you've got to convert, you've got to make sure you get to kilopascals. And if that's true, then basically this 8.314 becomes the constant, okay? And so that's going to be what you're going to use. Now, notice that I've shown here that you can rearrange that equation. You can get P by itself, you can get V by itself, you can get N by itself, and you can get T by itself just by rearranging. This is rearranging PV equals nRT, and so to get those unknowns. Okay, we're going to try a sample question in a second, but before we do, I want to just revisit one last topic before we do the sample question. And basically, the question I'm asking here is, what is the volume of 1 mole of oxygen gas? Well, that's interesting because I know my equation for volume is V is equal to nRT over P. That's just rearranging the PV equals nRT. Okay, well, all right. Well, oxygen gas, here we go. It's at STP, so watch this. Volume is equal to, well, it's 1 mole, so it's going to be 1. That's for my N. My R is 8.314. My T, if it's at STP, My T is equal to 273.15, because remember, I've got to use Kelvin. And then I'm going to divide by the pressure, which is 101.3 kPa. All right, so when I type that into my calculator, 8.314 times 273.15 divided by 101.3 kPa. And I get a value of 22.4 liters. Okay. So the volume of 1 mole of oxygen gas would be 22.4 liters. Okay, so an oxygen gas molecule is it's just two oxygens bonded together, just like that. Okay, well, the second question I have is, what is the volume of 1 mole of C2H4? That's like a ethene gas. It's a carbon double bonded to a carbon, and then with these 4 hydrogens around it. It's called ethene. Okay, so it's got a few more atoms than oxygen gas, but it says what's the volume of it? Well, a bunch of students might look at it and say, well, the volume's got to be bigger because that's a bigger molecule. Well, let's try it. So the volume is equal to 1, that's the number of moles, 1 mole, times 8.314 times 273.15, that's the temperature at STP, divided by the pressure, 101.3. Oh, it's the same equation. So guess what? It's the same volume. So interesting, the volume of a mole of gas doesn't change, even though this is a bigger molecule. Well, what if it was this huge molecule? What if it was like 75 carbons? Like, oh my goodness, it's like this huge, it goes on, 75 carbons plus 152 hydrogens. It's got all these hydrogens coming off of it. Guess what? Its volume is 22.4 liters. The size of the molecule doesn't impact the volume. Now, having said that, do all these containers have the same mass? Absolutely not. The mass depends on the molar mass. So remember, if you wanted to get what this container weighed, you'd have to go, well, the mass is equal to the number of moles times the molar mass. So for oxygen, it would be 1 times 32, because that's the molar mass of O2. So guess what? That container, even though it has 22.4 liters, it would weigh, assuming that the container didn't weigh anything, the amount of gas in the container would weigh 32 grams. Okay, well, if I did it for this second one, I'd have to do the molar mass of ethene. Well, guess what? It ends up being 28 grams. Okay, it's less because each carbon is only 12 and each hydrogen is 1, so it actually has a lower molar mass, even though it looks like a bigger molecule. And if I did it for this molecule, C75H152, the mass of that container would be 1,052 grams, so much, much heavier. So even though they all have the same volume, they all take up the same amount of space, they have different masses, okay? But what we call that 22.4 is the molar volume. It is the volume of 1 mole of gas at STP. Okay, and we know that the molar volume is 22.4 liters for any ideal gas. Okay, so any gas, regardless of the size, even though they're going to have different masses, will take up the same amount of room. Now, I hope some of you are struggling with that, because I just want to, this is a little section out of your textbook that I think explains it very well, and this is the question is, well, what do you mean? What's an ideal gas? What does it mean to be an ideal gas versus a real gas? Okay, and so do gases really take up, does 1 mole of every gas really take up 22.4 liters? Well, I'll just read this with you. It says, do real gases always behave like ideal gases? At STP, you have seen that most real gases do behave like ideal gases. At high pressures or low temperatures, so I'm going to underline this, at high pressures or low temperatures, however, gases no longer behave ideally. To understand why, recall that the characteristics of an ideal gas, according to the kinetic molecular theory, so listen to this. We studied the kinetic molecular theory yesterday. We said gas molecules have an insignificant volume. So in other words, the volume of the gas molecule doesn't impact, is insignificant compared to the volume of the container. Molecules have no attractive forces between them. Okay, molecules move in perfectly straight lines, and collisions are completely elastic. They don't use up energy. So these were the kinetic molecular theory. So these characteristics led to what we call the ideal gas law. That's basically that PV equals nRT. Okay, so we needed the kinetic molecular theory to prove this. They are accurate enough for most applications. However, they are not perfect. In fact, most gases fall short of these characteristics in many ways. The particles of real gases have a significant volume of their own. Molecules do attract each other. Molecules do not necessarily move in straight lines, and collisions are not completely elastic. So where it becomes most noticeable is at high pressures and or low temperatures. So at very high pressures and at very low temperatures, gases have smaller volumes. In other words, they no longer meet that 22.4 ideal. This means that gas molecules are closer together. Since they are closer together, the molecules interact more than when they were far apart. It is no longer true to say that molecules have no attractive forces between them or with their container. Okay, so all I'm saying is that at some point, for most situations, gases can be assumed to react like ideal gases. But however, at very high pressures and low temperatures, some of those kinetic molecular theory points stop being accurate, and so this equation becomes less valid at that point. Okay. Here we go. Here were some questions. Here, let me do one as an example. What I'll do is I'll just move these ones to the next page. Okay, so you guys can do 13, 14, and 15 for homework. Why don't we all do this one together? So here we go. Number 12, it says you've been given 4 liters of ammonia gas. So I'm given a volume is equal to 4 liters, and it's ammonia. So ammonia is NH3. It's a container that holds 2.17 moles. So I've been given the number of moles is 2.17 moles, and it's at a pressure. It's at a pressure of 206 kPa. So notice. Here, I'll just finish it. It says required, what is the temperature inside the container? So notice that in these questions, they don't give me 2 different states. So I'm hoping that they feel a little bit different than the questions you did for homework, where often you were given, well, if you start at a pressure and a volume of this and then increase the pressure to this, what's the new volume? Well, in that situation, it's a Boyle's law question. P1 V1 is equal to P2 V2. Whereas this one, they only give you one state of everything. But look at this. We know that according to the ideal gas law, PV equals nRT. And so we also know that R is equal to 8.314. So if we're solving for temperature, temperature is going to be equal to PV divided by NR. So double check that we have the right units. We have kPa, we have moles, and we have liters. Perfect. So this is going to give us an answer in Kelvin. So 206 for the pressure, a volume of 4 divided by 2.17 times 8.314. Okay, so 4 times 206 is equal to 824 divided by 2.17 divided by 8.314, and you get 45.7 Kelvin, and I could add 273.15, and so that is equal to 318.8 degrees Celsius. Let's double check how many significant digits. I'm only allowed 3, so it's probably 319 degrees Celsius. Let's check the answer in the back of the book. This was question number 12. Let's go to the answers here. And the answers for 12 is 45.7 Kelvin. What did I get? 45.7 Kelvin. Okay. All right, so just a few questions to finish off there, practicing working with the ideal gas law. Can you guys do 13 to 15? Let me know if you have any questions.